Hi, everyone. Can you all hear me OK? Hands up at the back if you can't hear me. Joke never really works particularly well. I'm sorry about that. Hi, everyone. Excellent. All the slides are up. My name is Simon Stewart. I'm an engineer in the recently formed London office here. I'm one of about 30 people, 30 engineers who work there. I work on the internal tools team. And my focus is on developer efficiency and effectiveness. And my particular focus is on enabling mobile developers and Android developers in particular to go as fast as they possibly can. I assume a lot of you are Android developers since you're here, right? Good, excellent. If you're an iOS developer, you're not going to get a lot out of this, I'm afraid. So, bit of scene setting. Let's go back, all the way back to 2012. It's a long time ago, I know. I can barely remember it. I can barely remember yesterday, to be fair. So 2012, early 2012, the Facebook app that you had was really convenient for Facebook. We were a web company, right? We were used to releasing software every day. If we pushed something live and there was something wrong with it, it was OK, because tomorrow we could fix it. And we could fix it globally for every single user of Facebook. And that was a really useful and powerful thing to be able to do. The problem was that the way we did this is we used WebView components in both the iOS and the Android app. Now, the WebView component is really useful because it allows you to render all this HTML content, which, as Jackson pointed out, you can make perform relatively well. But it has downsides. The first one is you lose some of the sort of niceties of a native application. So you lose some of that scrolling, that bounce in iOS, the attractive blue lines on Android, things like that. And the second thing is the JavaScript engine is pretty awful. If you've got a Jelly Bean phone, you've probably got, or an ice cream sandwich phone, like many people here probably do, you've got Chrome as your default browser on Android. And the JavaScript engine in that absolutely screams. The browser in that is phenomenal. The WebView doesn't use Chrome for rendering HTML, and it doesn't use V8 to run JavaScript. It's slower, less effective. And that meant that we've got a really poor user experience for our users, right? And the thing that's most important is that our users are happy, and our users have a delightful experience. So mid-2012, there's the infamous quote from Zuck where he stands up and he goes, probably the biggest mistake we made was using HTML5. And that isn't that HTML5 isn't good, it's just that it isn't ready yet to give the sort of user experience that we want to give our users on native. And we decided to go mobile first, and we decided to go mobile best. How did we do that? We took our engineers, who were writing PHP at the time, and we ran them through courses. We taught them how to write code for Android. We taught them how to write code for iOS. And when we had new hires, we made sure that these were people who were familiar with the mobile operating systems that were out there. And I think you can guess from this chart where that happened. If you're in the center row, it's there. That sudden inflection point, right? Now, there's approximately 1,400 engineers in total at Facebook. Not all of them contribute to the code base, but there's a sizable majority who have now written mobile code at Facebook. And it's likely you've got some of their code on your devices. An important thing to know here is there is no Android team anymore. What happens is we've got feature teams, right? I think this is one of the places where we're different from normal companies or smaller companies that I've had the fortune of working at. Some smaller companies will have an Android team, an iOS team, and a web team. We don't do that at Facebook, partly because we've got lots and lots of people who can write features on the web, and they go incredibly quickly. And if you have 20 people desperately trying to keep up with the better part of 1,400 engineers, what happens is one platform surges forward, and the mobile platforms tend to languish. Or worse, or perhaps nowadays better, the mobile platforms leap forward, and the web languishes. Either way, it's a suboptimal experience for your users. What we want to be able to do is offer a consistent experience across mobile, the web, and the mobile web. And the way we do that is we allow feature teams to own their feature over every single platform. Now, that probably means that the feature teams have people who are specialized in Android, specialize in iOS, but they own their feature across every single platform. And if they decide that they're not going to ship on a particular platform, they're going to have to answer to that. They're going to have to provide a really good reason for doing that. So there is no Android team who's desperately trying to keep up. What we have is we have feature teams who are focused on developing their feature for every single platform and all of our users. So, that's a bit of context. That gives you an idea of where we were, where we are. What's it like to actually be a developer at Facebook working on the Android app? Like, you're all here to hear how we build Facebook for Android. How do we build Facebook for Android? Well, the first thing is we actually build the code locally. In order to do that, we need to check the source code out of our source control system. We use a DVCS, Git, and we check into a central repo. Git is wonderful. It's really nice in that you can work on a local branch and then you can submit up. But globally, in the master repo, there are two branches that we care about. The first branch is master. And master contains the most up-to-date version of our source code. It's brilliant, right? Every single change that's been approved has gone into master. And it's great, and we have no idea how good it is. And that's why we have the stable branch. The stable branch is a branch where we've run every single test that we can throw at it, and we're fairly confident that the code in there is not only in the code base, but also solid and works as intended. How do we organize our code? Our code is organized in a single tree. There are lots of different ways of organizing your code base, but we value speed and we value effectiveness, and we really dislike boilerplate code. So what we've got is we've got a single tree with effectively 4 directories at the top of it. First directory is called Java, contains our Java code. Guess what's in Java tests? No one's guessed, but I imagine you all know, right? The Java tests are in the Java test directory. Third party contains third-party libraries that we depend upon. And we've also got a directory for assets that are used for our Android apps. Now, the interesting thing here is we've got one tree that's shared by every single application that we write for Android. So Instagram, the Facebook for Android, Messenger, the Pages Manager, you name it. If we ship it as an application for Android, its code is in that tree. There are a number of advantages to this, but the main one, the thing that I think is really crucial, is it makes it really easy to share code between applications, which means if we identify a bug or regression in a core library that's used across multiple products, and we fix it for every single app that uses it. Makes it easy to share the code, makes it easy to move things from a single project into the global tree. It's really nice. It does mean that the code tree gets pretty big, but we'll cover how we cope with that later. So your daily workflow looks a little bit like this. You pick up one of your list of tasks, and it's like, hey, develop some new fancy feature. So you do a git checkout, you create a new branch, you hack it away at it, you create a new commit on your local working copy. During the time that you've been hacking on things, what's probably happened is that other people have been developing, 1,400 engineers. Hopefully somebody's checked in the time it's taking you to write some code. So we rebase onto the stable branch, and we continue hacking. And we reach a point where we think, actually, I think this is OK. I think I'm ready to have this reviewed by somebody. So we commit a checkpoint, and then we do something that's quite unusual, or it might not be unusual. We collapse our diffs into a single diff. So what we want to do is when we check into master, we want a single logical change to be landing into master rather than the intermediate steps that we took to get there. And there are 2 really good reasons for this. The first one is that if I'm trying to follow along at home about what everyone's been working on, it's a lot easier for me to reason about it and to understand what's going on if the commits that go in are single logical changes that represent a new feature or a bug fix, rather than the individual steps that somebody took to get there. The second reason is that if there's a problem and we need to yank your change for whatever reason, pull it out of master so you can fix it. Maybe you broke a continuous build or something like that. It's a lot easier to pull it out if there's only one diff to remove, rather than 5 or 6 diffs that are interleaved with a bunch of other people's work. So it's really useful. We like to collapse down to to a single change. And finally, we run arcdiff. I'll cover what that does later. So you're writing code, right? We use IntelliJ as our IDE of choice. It's a lovely IDE. Eclipse also works, but everyone uses IntelliJ. And there are some design patterns that we encourage people to use. We like to move fast. We like to be able to prove to ourselves that our code works. And one of the ways that we can move fast is by not spending a lot of time fixing bugs. So testing is really important to us, right? And one of the patterns that we use to improve testability is a pattern called Dependency Injection. Has everyone here heard of Dependency Injection? A couple of hands going up. OK. So there are two ways in an object-oriented system that a class can access its collaborators, right? The things it needs to interact with in order to do things. The common two patterns that you see, one's called service location and dependency injection. First, service location, typically implemented using singletons or perhaps some sort of registry of objects. Midway through a method, you go, I need a new database connection. And you go to your collection and you go, give me a new database collection. And it goes, here you are. And it's brilliant, right? And you use your database connection and everything's good. Dependency injection, your class declares somehow, perhaps in a constructor, perhaps in a setter, perhaps on an annotated field, that it needs a database connection. And at instantiation time, or when we create the object, we pass in the particular thing it claims it needs. How does that improve testability? Well, the thing is that if you treat your class as a black box, if you have no idea how it works, with service location, you have no idea what it collaborates with. If you're trying to write a unit test around it, you have no idea what's going on. With dependency injection, you can just look at the arguments in the construction, and you can say, hey, look, it needs one of these. So it's super easy to substitute a collaborator at runtime. So we're big fans of dependency injection. Now, the thing is, our code base is big. We appreciate speed. How do we build quickly? We use a custom build tool, which we call Buck. Why did we write a custom build tool called Buck? That's an excellent question. So one of the reasons is, like I said before, we appreciate not having a large amount of boilerplate code in our code base. If we're using a system like Maven, for example, the way that we would have all these interdependent modules that we have is we'd have a series of top-level libraries, and they'd each have a certain number of directories and libraries and a pom.xml, and they'd be hooked together, and it would be a nightmare. Worse, because it's so onerous and difficult to set all that stuff up, what tends to happen is that engineers, rather than doing the right thing, tend to just clump everything together. So you end up with a small number of relatively large individual modules that aren't particularly well factored. And that's not a nice place to be. So we want to minimize the overhead in creating a new module, and we want to keep the boilerplate out of our code base. We also want things to be IDE friendly. We're huge fans of IntelliJ. If you're Java developers, if you're working on Android, you know that this tooling gives you amazing power, like the ability to think in just the refactorings you're applying to your code base. It's one of the reasons why I still appreciate programming in Java, even though there are far hipper and trendier languages out there. So we want to be friendly to an IDE. We want fast, clean builds. So if you check out the code, you run clean, it should be incredibly quick. But more importantly, because running a clean build indicates your build system has no idea about the state of the world and has lost track of something, and you're not confident that it's going to do the right thing, running a clean build is a bug in your build system. Your incremental builds should be incredibly rapid as well. That's really important. And finally, no build system really understands the crazy things that developers will want to do. We want to support adding ad hoc steps midway through. So that's why we wrote Buck. There are three important concepts in Buck as a build system. The first one is a build rule. You can think of a build rule as a procedure or a function for taking input files and converting them into, at most, one output file. We declare these build rules in build files. Now, these build files are called Buck by convention, all capital letters. And these are scattered in a hierarchy through the code base. And finally, we can refer inside a build file to other build rules using build targets. So that's like a label pointing towards a particular build rule in a particular build file. It's a string identifier. Build target looks a little bit like this. It looks slightly odd, unless you've used Twitter's pants system, or if you're on the Selenium project, we use something very similar as well. But this is pretty easy to read. The double slash means, sorry, I'm standing in front of it here. The double slash means from the root of the project directory, so from where the .git directory is, there is a directory called JavaCom Facebook Share, brilliant, colon, in which there is a buck file containing a build rule called UI. Okay? So this allows you to uniquely identify any particular build rule anywhere in the tree. And we hook these things together in our build rules. So this is a standard build rule. This is for building a library, a Java library specifically for Android, so we know we can dex it, we can do all sorts of fun things with it. It's the UI library. Sources, we do a recursive glob. Now, that's not a recursive glob of the entire file tree. Right? If you've used Ant, you sometimes see like people going glob from ***, and it'll just eat everything, right? This is from the directory in which the buck file resides. So everything from there and below. So we pick up all the Java files. As you can see, we've got dependencies using that build target specification, which we just talked about. And we've got this weird thing called visibility. So by default, any build rule is not visible to any other build rule in the system that's not in the same build file. Okay, so that's kind of a pain in the backside. So what you can do is you can annotate each rule with a visibility. If it's public, anyone can access it. It's a free-for-all. But you can limit it to particular build targets. And that's really useful, right? Because what it allows you to do is it allows you to have a module in your system with a well-known name, but you can package it up and you can organize it and you can arrange it in any way you want to. And everyone just needs to depend on that well-known name. In order to make sure that people pick up the whole of that library as you intend it to be used, you can do a thing called export deps, which isn't here, which just allows you to say, you can depend on this, and what will happen is we will export transitively every single dependency of that library to anyone that depends on it, which is kind of nice. Sounds like magic, right? How do we do all this stuff? Well, the build rules in this completely declarative build system we have are written in Python, which is a Turing-complete language. There's one person who cheered at the back there. Now, this is really nice, right? Because we don't actually have every single build rule in the system. We don't know everything that everyone is going to do. But what we do is we allow people to add the missing pieces themselves while we're working on integrating that into our system. So the build file allows you to do, the build files allow you to do simple things like, hey, perhaps every single rule should have Google's Guava library as a dependency because it's just used globally, right? And you can say, hey, that's what we're going to do. Or you can declare a new build type, a new build rule, which will expand out to be a series of other rules that are already extant in the system. So if you wanted to do, I don't know, a Mozilla zippy, an XPI file, for example, that's just a zip file with bits and pieces arranged, you could do it pretty easily. So you've got all these build files, and basically they end up pointing towards building a directed acyclic graph. Now, I did computer science at university. It's very rare for me to be able to use terms like directed acyclic graph. I don't know about you guys. The only thing that I use less frequently than terms than that, things like big O notation. So I'm just going to enjoy saying directed acyclic graph. So you got this, I got this DAG, and that's fantastic. And the nice thing with a directed acyclic graph is it doesn't actually have a root per se. There are subgraphs within that where you can pull out a single node and you can go, hey, look, this is what we'll do. So what Buck does is when you run a Buck build, we run as much stuff in parallel as possible. We take our graph, we apply a topological sort to it, we identify cycles, we bail if we spot a cycle, but otherwise we spin up however many builders we can. How many builders do we make available immediately? Well, what we do is 1.25 the number of cores reported by Java, which is a bit of a strange number. In more practical terms, a modern laptop probably has a Intel CPU with 4 physical cores on it, but you've probably got hyperthreading, and hyperthreading makes it appear like you've got 8 cores. 1.25 times 8 is 10. Yes. So we've got 10 simultaneous builders going at the time, and there's nothing a user has to do to enable that parallelism. It'll just happen for them automatically when they're using Buck, and that's an enormous win. If you've used a system like Ant, you've got to like mark things as running in parallel. It's kind of a pain in the backside. How does IntelliJ feel about all this? Feels pretty good about it. We've got a command called buck project, and what that will do is it'll lay out the IPR and IML files so that you can just point IntelliJ at the directory containing your .git file, the root of the repo, and magically it'll go, yeah, I understand this. Everything will load. You'll have all your modules laid out. It's fantastic, right? So you can get started. We focus on speed. An example, recently, while I've been working on at Facebook, which has only been sort of really this year, we enabled parallel builds using Buck. So we used to have just a single thread of execution, even though Buck was capable of running in parallel. And we noticed that our build times were bloating out, and they hit 20 minutes. We went, this is enough. We did a small amount of engineering work. That is, we increased the number of threads, and we went from 20 minutes to a 4-minute build time. That's fast, right? That's a significant saving. When you spread it out over the engineering force at Facebook, that's saving days of developer time every day. Our incremental builds. We used to use timestamps to identify whether or not we needed to rebuild things. Turns out that's inefficient. If you do a git checkout of another branch, if you do a rebase, although the files are identical in their content, maybe the timestamp has been updated. Maybe you go to somewhere, you edit it fairly high up in the hierarchy, right? You add a systemout.println, and you go, actually, systemout.println is awful. I'll delete that line. You return the file to its original state. If you're only using timestamps, an incremental rebuild will just go and rebuild far more of the tree than it needs to. So we do content-based hashing to identify whether or not we need to rebuild a particular rule. And that means our incremental builds are blazingly fast. And we're focusing even more on speed. Currently, a no-op build of our build tree takes in the region of 20 to 30 seconds, depending on how fast your SSD is. Our tree is fairly large. We'd like to slash that to almost instant. One way to do that is to just keep an eye on the file system, monitor it, and when we notice that particular pieces have changed, either update our build graph or invalidate particular rules so that when someone says do a build, we can start building rather than having to figure out what the heck it is that we need to do. And the other thing is, we've got lots of people who are probably checked out at the same revision as you. Everyone is basing themselves off stable, right? So if that person over there has already done a build, why can't you use the artifacts that they build? So we're working on a distributed cache to enable us to go even faster. Like, the fastest way to build something is to not build it at all. So how fast actually is Buck? When we flipped the switch from using the previous build tool, I think it was Ant. This was before I joined Facebook. I think we were using Ant. It was taking 3 minutes, 40 seconds to do a build. And what we did is we added a little echo statement at the beginning of the build that said, you know, you should go to this directory, check out this, and you'll be away. It was possible to check out Buck onto your local workstation, build Buck, and do a complete build of the project using Buck before the original Ant build had finished. That's how much faster Buck was. Can we flip to the laptop, please? I'm going to enter my top secret password. So I've been talking a lot about it, right? But there's nothing quite like seeing speed, right? So this is the Buck source code. I'm going to, can you all read that, by the way? Can you read that at the back? Can you read it now? Like it's gargantuan now. So this is Buck built using Ant. So we're doing a clean. What we're going to do is we're going to compile everything, and then we're going to run the tests. Has anyone used Ant before? It's pretty boring when the tests run, right? If we were to look at the activity monitor, what we'd see is this ultra-powerful laptop is barely even ticking over, right? There's nothing particularly interesting going on. So I'll move that down there. It never actually got to the end, and I gave it about 30 seconds there. So what we're going to do now, we'll do the same thing with Buck. We're going to just do a clean, and then we're going to test every single test in the system. Keep an eye on the CPU monitor down at the bottom of the screen. I'll lift it up. You'll see that already we're making better utilization of the machine. And it's just run every single test in the project and done a complete build in under 14 seconds, which is actually fairly nice, right? To do that using Ant, I have no idea how we'd have done it. It would have required a significant amount of engineering. Can we flip back to the slides, please? So yes, Buck, blazingly fast, fantastic. And the good news is you can use it too. This is the tool that we use for building Facebook for Android. This is the tool we use for building Messenger. This is the tool we use for building Instagram. This is the way that we build software at Facebook, and you can use it. The code is available on GitHub. We've done a slightly unusual thing, and we've included documentation, so you can actually understand how it works. It's under a nice Apache 2 license, so if you're trying to pull this into a company that's worried about various bits and pieces, you can do that. The majority of it is written in Java, right? It's an Android build tool. You should be able to go in there and tinker with it yourself. You all write Java for a living. It's easy to go in and fiddle with it. There are bits of it that are written in Python. Python's a nice, friendly language. There's a cheer at the back for it. At the moment, I'm really pleased by that. You can't see this on the cameras, but every laptop that's open is a Mac. And that's a really good thing, because at the moment, it only runs on OS X and Linux. We have plans to get it running on Windows, but it turns out that none of the developers at Facebook who are working on the Android apps develop on Windows, so we've never had to do it. And it's not self-hosting at the moment, so we build Buck with Ant, because it seemed like a good idea at the time. So, Buck, go, download it. Pull requests, by the way, really happily accepted. Bug reports, also accepted, and we'll pretend to be happy about them. You've written the code. We now want to test it. One important thing here is that our developers write the tests. There's no QA department. There are no software engineers in tests. There are no SDETs, I think is the Microsoft term for it. Our developers write the tests. What kind of tests do they write? Well, they write unit tests, right? A unit test is small. It executes extremely quickly. And what we like to do is we like to keep everything on the local JVM. We don't want to have to compile class files, build jars, and then cross-compile using to Dalvik, and then push onto a device or an emulator and run a test on that. That's slow. Running in the IDE immediately, Control-Shift-F10, that's fast. All right? So we use a library called Roboelectric to enable that. Roboelectric replaces the stub classes provided by the Android jar with working implementations. So you can keep things local, even if you are using Android classes. If you haven't had a look at it, do take a look. I recommend it. You remember I talked about dependency injection and how awesome that is? Well, we use EasyMock to allow us to quickly replace classes at runtime in our unit tests. And of course, Kent Beck works at Facebook. It's only polite that we use JUnit to run our tests with. Problem is, with unit tests, you don't always know whether or not the app works. Before I joined Facebook, I worked on a project once which had 2,000 to 3,000 tests. The tests ran in a handful of seconds. It was truly impressive. Problem was that the app never started because people were just making things up in their tests. The mock objects they were using would return null when in reality they threw an exception, or vice versa. So you do need larger tests. You need integration tests and you need end-to-end tests. We're still exploring how to do end-to-end testing effectively. We started with Robotium, but I think we're heading towards a custom solution built on UI automation, which is available in ICS and above. And I think that's going to be a winner. We also use things like the monkey runner and just any tool that's available to us, right? What we do is we also run tests that on emulators as well as on actual devices. Quick tip here, emulators have got a lot better since the days of Froyo. When I was doing Froyo development, it was awful, right? The emulator had almost no resemblance to reality. Nowadays, the Jelly Bean emulator is really good. If you get the x86 images and you install the Haxum extensions, you'll have a device that is actually faster than an emulator that's faster than a device, which is really cool. So you tested your code, you want to land it, right? You want to commit it. You remember that arcdiff that I spoke about before? That's our gateway to Phabricator. Phabricator is like a Swiss Army chainsaw of project management stuff, right? It's got code review tool, wiki, task tracking, you name it, it's in there, right? We use it for code reviews, and we use it extensively. Every single line of code that lands in the Android code base has been written by one person and reviewed by at least one other person. 2 eyes have been on every single line of code that goes into the code base, which is one of the reasons we can get away without having a formal QA department, because people spot other people's thinkos. Code review tool, pretty basic here. You can see the guy has put forward what he's planning on doing. In purple, there's his carefully blurred out test plan. You'll see it's extensive. We like extensive test plans. If your test plan is meh, or the written equivalent, it tend to send it back and go, must try harder. You'll see here that someone's given some feedback. It's hopefully been responded to. And then right at the bottom in green, hey, look, it's been accepted, right? It's a fairly standard code review tool. The killer feature of Phabricator, and one of the reasons why I really enjoy using it, image macros. You can litter your review with these image macros, right? I have no idea what Obama playing a bald eagle guitar actually means, but I do know what ship it means. I'm sorry, I find it fascinating. I find it hard to tear my eyes away from that. Not in a good way. So, you've got your green, you've got your go-ahead to ship the code. What do? You run a command called arcland. Arcland does 2 separate things. First thing it does is it runs a linting phase, which you can run using arclint. So for those of you who can't read the slide, Arcanist is a command line counterpart to Phabricator. The 2 work hand in hand. Arclint, when we run the linting checks, are using Android's own lint built in, and we check for things like null pointer exceptions or using APIs that aren't available on Gingerbread. And finally, it lands it. That just copies your changes from your branch onto master, pushes to master, deletes your branch. So you've got a nice, clean working copy. Once it's up in the working copy, our continuous integration system, which is based on BuildBot, picks it up and runs a battery of tests that we think will take too long for a developer to actually run themselves. So this is where we do things like power regression testing, where we do our end-to-end tests, things like that. As you can see, most of the time it's good, except occasionally a developer does naughty things and a build fails. We dog food constantly. One of the reasons we dog food is because of Gingerbread. Gingerbread is still wildly popular. It's something like 44% of the market at the last market share. You can't ignore it as a platform, but you don't really want to have to use it day in, day out. And that's why certain Facebook employees have volunteered to use Gingerbread as their primary device, so they can dog food the latest version of the app on that. And one of those volunteers is the Android release manager. He's not always happy. So what we do, we sideload the current beta version onto the app, onto your device, if you're a Facebook employee and you volunteer. And every day, we do a check to see whether there's a new version. If there is, we download it in the background and gently nag you to do an update to that latest version. So employees use a more recent version of the app than the public do, and that's cool. And if there's a problem with it, they can shake their device. We call it a rage shake, because normally you run into a problem and you go, it's not working. OK, now it's good. And that allows you to file bugs, which allows us to do a release. So, we've been talking about the path for developers, but there's a bunch of other things that need to happen before you can call a particular feature done. If we see design work going in when we're about to cut a release, we know a feature isn't complete, right? There's still work to be done on it. We need logging to be in place so we can catch regressions. If there are server-side changes, we need to ensure that it works with the new version of the app and the old version of the app. That's really important. And we care deeply about people's privacy and ensuring that we haven't done anything which is sketchy or odd, right? We rely on people's trust as a social network. Privacy matters to us very much. So done isn't just about native code. When you're doing a release, you've got 3 variables that you can play with: features, quality, and the schedule. And you can pick any 2, and the third one, I'm afraid, has to flap in the wind, and it'll be whatever it is. The 2 that we pick are quality. No release should ever leave a user with a worse version of the app than they currently have. And we value a schedule, a regular schedule, because if you do feature-based releases, you have no real idea when the next version is going to go out the door. So we do time-based releases. Now, the nice thing with this is you know that if you get your feature into ready for release, it'll go out there on a certain date. If it's not ready, that's fine. There'll be another release soon. And you also know you're not going to be held back by someone else. We do a release every 4 weeks. So every 4 weeks, we cut what we call a release branch. And that's always a fun day, the day that we cut the release branch. We cut the release branch. We do 3 weeks of stabilization work. And we spend a week doing release candidates. And then we finally push it to the Play Store. And that's where everyone downloads it. I think, what was it? 751 million people day by day using mobile. That's a really impressive number. Very, very large percentage of those are using the Android app. So that's how we do, that's how we build Facebook for Android. Got a few minutes left over for questions. I know I just blistered through an awful lot of stuff, so feel free to just circle back and ask me anything about anything that I've spoken about. In fact, feel free to ask me anything, right? I'll do my best to answer. There's a gentleman there in the blue shirt.
Hi, my name is Ben.
Hi, Ben.
I would like to know what kind of logging you use in the app.
What kind of logging?
Yeah, you use some, yeah.
So I'm not quite sure of the way that of the tooling that we do, but we do keep track of things like crash rates. So if we push a new version of the app to the outside world, and we suddenly see a spike in crash rates, or if we see that in our betas, we know that something has gone horribly, horribly wrong. One of the problems that we see quite often is we test quite a lot on ICS and Jelly Bean devices, and they tend to have oodles of memory. What happens is when it goes to Gingerbread, we quite often see out-of-memory exceptions that happen. I can help you later find someone who's working on the Android app itself to try and find out sort of more about the logging, if that would help.
Yeah, cool. Thank you.
Cool. OK. Next question. There's a guy there's a couple of people over there.
It's actually going to be our last question.
OK, it's going to be one last question, but I'm going to be around, and I'll be here in office hours as well, so feel free to find me. It's always questions at opposite ends of the room. I always find that. Thank you very much. We're waiting just for the microphone, and there we go.
Hi. I was just wondering, how do you handle the image resources for the different resolutions in your build system?
So we're the buck allows us to separate bits, our resources into different folders, right? And we can construct the r.java at build time, which is kind of nice. And then what we do is we have separate targets for each of the display resolutions. So you can build either with all the images in or with just a particular set of resolution images available to you. Again, bizarrely, right, I work on the tooling, so I know how it's built, but I don't know what people are doing with the amazing tooling that we've given them. But I can help you find someone who can help answer that question in a bit more detail later on. Cool. OK, thank you very much. Thank you.
All right, change of pace. In the other room is now the partner panel, followed by the office hours. So I would head next door and get a seat. Thank you.
How was that?
It was awesome.